we have 4 more minutes to spare, but I guess Alexei is, are you available? If you want to start now?
I am here.
Awesome, cool. So let me introduce you. So it's my great pleasure to introduce Alexei Baevski. He is a research engineer with us at Meta AI. Previously, Facebook AI research, working in natural language processing and speech processing problems with great work, most notably, of course, amazing work in self-supervised learning in speech and language and vision. Recently, the Vivek, he has been actively contributing and maintaining toolkits like FairSeek, which we all use, and it's amazing toolkit on top of PyTorch. And he is the author of the series of papers of Wave to Vec 1, 2, Wave to Vec U, and VQ to Vec, and more recently the to Vec. So so excited to listen to Alexei's presentation. Please go ahead.
Thank you so much, Abdo. Really appreciate the great introduction. Let me share my my presentation. Here it is. Okay, so in this presentation, what I'd like to talk about is our newest work, which is data to Vec, and specifically I'll focus on application of data to Vec to speech. This is the recent work that just came out a month and a half ago, so it hasn't been peer reviewed, but the preprint is available on arXiv, and we've also released most of the code in the models, and it's publicly available. All right, so what is, sorry, just 1 second. Okay, sorry about that. Okay, so what is data to Vec? So data to Vec is an attempt to make a generalized self-supervised learning algorithm that works on different modalities in the same way. So far, we've tested it on audio, images, and text, and we found that applying it to those modalities achieves state-of-the-art results in a like-for-like setup on tasks like speech recognition when measured on Libri speech, image classification when measured on ImageNet, and it's also competitive to leading algorithm on text classification tasks when pre-trained on text data. At the core of data to Vec is a self-distillation setup. It uses a momentum teacher to generate contextualized targets, and it learns, and the model trains by reconstructing them to solve a math prediction task. So I'll give more details about this in the future slides. Next, I'd like to talk about what is the motivation for building an algorithm like data to Vec. So the hypothesis that we started with is that a good self-supervised learning algorithm learns representations that are both contextualized, meaning that the target or each representation of a portion of the data also is specific depending on the context surrounding that time step. And also that it is predictive, meaning that you can use a representation to infer unseen data from the same sample. We also wanted to design an algorithm that works on any kind of data that is structured. So that means you can split up your sample into segments. For something like speech or text, this comes naturally as the data is temporal in nature. And for something like images, you can split it into patches, right? So you can build a grid out of an image. Most of the current leading self-supervised learning techniques are based on predicting or reconstructing local input. So examples of this are BERT or Wave to Vec 2.0 or Envision MAE, which is also a recent work, or learning a representation which is invariant to data augmentations. And I'll discuss examples of these two approaches shortly. So the question we had was, can we do better? Can we combine the useful techniques in one algorithm? The inspiration for this work was 2 or 3 very important works. So one was Hubert that also came out of Meta AI, and this algorithm actually is one which learns contextualized representations, and it does so by clustering intermediate transformer representations. And we'll go a little bit into more details on how Hubert contributed to our work in the next slide. Another inspiring series of works were Bring Your Own Latent from DeepMind and Dino from Meta AI. These algorithms were designed for self-supervised learning for vision, and they learn data augmentation and invariant representations, and they do so through a self-distillation setup using a momentum teacher, which is what data to Vec does as well. So Hubert was really one of the most inspiring works for data to vec. I'm sure most of you are familiar with Hubert, but just a quick recap. Hubert uses a very similar architecture to Wave2Vec 2.0, but it changes the task to be a mask prediction task instead of contrastive learning task. And the targets for Hubert are cluster identities, which are discrete. In order to construct these cluster identities, it first builds targets from clustering MFCC features, trains the first iteration of the model. This kind of model uses local, the targets are local in nature. However, subsequent targets are clustered from some layer in the previous, from the transformer model from the previous step. This layer is identified through a small supervised selection step, layer selection step. And these targets are actually contextualized because they're obtained from a model which has access to the entire context. So, Hubert performs really well, both for speech recognition tasks as well as other tasks as measured on the super benchmark. BYOL and Dino, as I mentioned, are algorithms for self-supervised learning and vision. And the way they work is they take an input image, they apply different data augmentations to the same image. One of the instances is passed through a so-called teacher network. This network is not updated through backpropagation, but this network constructs some representation, and the same sample, but with a different view or different data augmentation, is passed through the student network. This is the network which actually learns through backpropagation. And the goal of the setup is to for the model to build representations that are invariant to data augmentation. So the one produced by the student should be similar to the one produced by the teacher. This kind of setup learns very good representations. It also benefits from improving targets over time because the teacher is continually being updated by tracking the student through exponential moving average. However, one of the potential downsides of this method is that it relies on handcrafted data augmentation policy to choose what kind of how the data should be perturbed between teacher and the student. And there's also a bunch of tricks to make sure that the model is stable. All right, now we come to data to vec. I won't go into too much detail about all the nitty-gritty details of this algorithm, so I'll just give a very brief overview. The setup is so if you look just at the model architecture, and if you're familiar with prior work in self-supervised learning field for audio, text, or vision, you'll see that the architecture is very familiar. For data to vec, we have a modality-specific feature encoder. This means that for speech, we use a convolutional neural network, just like in Wave2Vec 2.0, to encode speech into latent representations. For text, we use just an embedding table. And for images, we follow a VIT setup where they have an MLP that encodes each patch into an embedding. Once you have these latent representations, you kind of follow the diagram above. So you mask a portion of the representations in latent space. So we never mask the original input, and we don't really augment the original input, although we may do so for regularization, specifically for images. The masking is done in a similar way that was designed for Wave2Vec 2.0, which means we do span masking, and we actually have to choose different masking hyperparameters, meaning how many representations or time steps do we actually mask, and what is the span length, depending on the modality. This is because something like text contains more information than speech, depending on how you parameterize your feature encoder, so the granularity could be different. And for vision, for images, you also have spans that are 2D in nature. So once you've encoded your input and once you've masked it, the rest of the algorithm works exactly the same. You have two copies of the same model. One is the student model being updated through backpropagation, just like BYOL or Dino. And then you have a copy of this model that is being tracked through exponential moving average. So it's not an exact copy, but something from the past. The teacher gets the version of the input which has no masking applied whatsoever. And then it produces some representations, whereas the student gets the version of the data with the masks applied. The goal of the student is to then reconstruct the representations produced by the teacher, which it has not seen. And then the teacher is updated through exponential moving average, as I mentioned. The context encoder network, the one that actually produced the student and the teacher after the feature encoder, is exactly the same for all modalities. It is just a regular transformer network, just like the one used for Wave2Vec or Roberta or the VIT models. The learning task is also identical. We're just reconstructing representations. How exactly we reconstruct is not too important. You can use your standard L2 loss, or you can use the smooth L1 loss or something like this. All of this works well. One key kind of insight that we had is that, in fact, if you just reconstruct the last layer of the teacher model, the accuracy of this approach is not going to be very good. You can see the ablation study on the bottom right. It kind of works okay for vision, but for NLP and speech, if you just reconstruct the targets from the top layer, it will actually not work very well. So what does work is averaging representations across multiple layers. As you can see in the ablation study, the K there is how many layers you average starting from the top. And then reconstructing this average representations. Why this is important is, I think, should be studied in more detail. But one hypothesis is that the transformer models encode data or begin by encoding local features in the beginning. Then, in order to solve the prediction task, they encode data into a more semantically useful form. And then close to the end of the model, they transform the data back into something that solves the task in hand. So like lowers the prediction loss. So if you want to learn features that are semantically meaningful, then you probably need to predict features from the middle of the model. And by averaging all of the representations together, we obtain a representation that captures different kinds of features, both semantic, local, and others. But as I said, I think more study here is required. Right, so this is in a nutshell how Data2Vec works. What are the results? So here we present results just for speech. And this is test other award error rate on LibreSpeech decoded with the 4-gram language model. On the left, we have a table where we pre-train a base model on 960 hours of LibreSpeech. You can see from pre-training updates, we compare the Wave2Vec 2.0 model, which was pre-trained for 400,000 updates. We also compare Hubert and a new model called WaveLM from Microsoft that came out recently. It is very similar to Hubert, but they modified the architecture to improve it a little bit. And finally, Data2Vec. You can see Wave2Vec 2.0 and Data2Vec are pre-trained for 400K updates, whereas Hubert and WaveLM require 2 stages, first training on MFCC features, and finally on clustered representations from the transformer. And you can see that Hubert and WaveLM work better than Wave2Vec. However, Data2Vec improves over prior work by more than 20% on 10 minutes of data, and the improvement still holds as you increase the amount of labeled data, although the relative differences diminish. In the table on the right, you can see the large model, the one that has 300 million parameters. We have not released the Data2Vec large model yet, but we will shortly. These models were pre-trained on LibreLite, which is a data set containing 60,000 hours of unlabeled data, except for WaveLM, which was pre-trained on additional data. They train, I believe, on a total of 96,000 hours of data. And again, if we look at the pre-training updates, Wave2Vec 2.0 was trained for 1 million updates. Hubert and WaveLM have an initial step, which is the smaller base model that was pre-trained for first 250K updates. And then the second iteration was pre-trained for 400K updates. And then finally, the large model for Hubert was trained for 400K updates. And for WaveLM, it was trained for 700K updates. For Data2Vec, we trained from scratch for 600K updates in total. And as you can see, the Data2Vec still performs really well with about 20% improvement over Wave2Vec 2.0 and Hubert for 10-minute setup, although the gains diminish as you add more label data. And by the time we get to 100 hours of label data, all models perform approximately the same. So what are some of the limitations of data2vec? It performs really well, but it still requires modality-specific feature encoder and masking parameters. It's also sensitive to hyperparameter choices. So if you choose wrong hyperparameters, the model can and will collapse during training, or the results will plateau. So meaning you'll get some relatively good result, by training, just a quarter of the time, but it might not improve after that. It also requires 2 forward passes during training because you need to obtain the targets and then you use the student to predict the targets. However, we can mitigate this by reusing the feature encoder output. So actually, if the feature encoder is not tracked, it is shared between student and teacher, meaning you can encode the input just once and then mask a copy of it and use the other unmasked version for the teacher. You can also encode fewer examples. So your batch size might be smaller, but then you can generate several permutations of these examples with different masks. And this also works really well, although that's not something we discuss in the paper. So there's mitigation strategies for requiring 2 forward passes. And finally, what is some future work to follow data2vec? Well, one obvious thing is recipes for additional modalities. These are things like videos, offline reinforcement learning, and so on and so forth. Another relatively obvious direction is modality agnostic feature encoders. For example, like those introduced in the perceiver line of work from DeepMind. A very common thing that people keep asking about is this a multimodal model, or is this a single modality model? I would call it the modality agnostic model because the task and the model is largely the same for each modality, except for the feature encoder. However, we still train on one modality at a time, and combining modalities using this algorithm would be really interesting. Finally, we can explore causal or generative pre-training using the same kind of contextualized targets that we introduce here, and we think this might also work well. This concludes my presentation. Thank you very much, and I'm happy to take any questions.
Thank you so much, Alexei, for your amazing work and amazing presentation.